Hello, everyone. My name is Jimmy Whitaker, and I'm going to be talking today about rethinking machine learning development, a data-centric approach. So just a couple of notes before we get started. I'll be kind of talking through everything that we have here, but we're going to be taking some questions at the end. If you have some questions as we go, feel free to pop those in the chat, and I'll try to make sure that I loop back around to address those at the end for sure. So so welcome in, everybody. Like I said, my name is Jimmy Whitaker. I'm the chief scientist at Pachyderm. And today we're going to be talking about data-centric AI and kind of the move to machine learning development, the move in machine learning and development to it. So our agenda is pretty simple. We're first going to start with a discussion on where AI is today. And then we're going to start moving towards or talking about the move towards data-centric AI and how this is actually making data somewhat the new source code and what this actually means for our development process. And then we're going to start spend the bulk of our time actually looking at some of the practical steps and some of the principles that sort of should guide our approach to machine learning, and even our guide to the approach of how we should set our machine learning goals and what we should be looking at to accomplish these things with kind of a regular speed and cadence and setting ourselves up for success there. So with that, let's get started. Also, if there's any mic issues or video issues or anything with the slides, feel free to pop those in the chat as well. All right, so let's start with where AI is today. So if we look at where we are today with AI and machine learning, we're actually still, in my opinion, still in the early stages. So if we look at the technology adoption lifecycle, this has been shared in a variety of books and resources and everything, but we seem to be pretty much past the chasm. So where there's usually early innovations, and then if they don't get adopted or enough early adopters, then people tend to fall off. But what we're seeing generally in AI and machine learning is that there's growth and development across many different industries. But the level to which people have fully adopted it, or adopted machine learning as a core discipline, is still relatively few. I don't know if you've seen this at your own industries or if you've talked to other people, but what we do know is that people who are using machine learning to accomplish certain things, who have worked to incorporate AI into their current processes and do different things with it, they are seeing success. So that's really exciting. But from a business perspective, these companies have achieved some amount of success with these early initiatives, and they're increasing their budgets for them. But they're trying to figure out how to best spend that money, because some of the larger companies who have been just adopters of AI for a very long time, they've already spent a lot of time overcoming some of the operational hurdles. But in some of the newer companies with economic downturn and everything else, they're trying to figure out how to best spend the money to actually reap the benefits of AI and machine learning, and how they can actually use this to best actually organize their internal systems and how to get the most value out of it during this process. So many of these organizations are specifically focused on the next steps of their AI journey. So they've seen a little bit of success with the most common applications of these budgets, or how they're trying to spend their money. They want to be able to increase the data and increase the process or their productivity of their processes that they're using to build models and roll them out. So one area that differs ever so slightly is the area of deep learning. This is usually for addressing much more complex set of problems, but only about 16% of companies, according to a McKinsey study, have been able to go beyond the piloting phase with deep learning and actually put things into production. So while that may sound a little bit like a negative, overall, I see this as a positive sign. It's really interesting that we're still in this early adopter stage. I think we see a lot of the companies that are coming out and a lot of the people that are working on many different things around the industry. It's actually a really positive sign, but we also see it as it's a little bit confusing. It's hard to navigate all the different things that are going on, even to navigate how we should structure internal processes and everything else. So overall, we're seeing that adoption of machine learning is gaining traction steadily, but we're still in this early stage where people are trying to figure things out. And one thing that I said here, the places where people are spending most of their budgets is on increasing and improving their data sets and their data quality, and increasing their process productivity. So how long it takes them to put a model into production or to generate a model itself. And so this has actually been one of the key things that has pushed people towards data-centric AI. So that's what we're going to spend a lot of today talking about, is data-centric AI. So with these trends and budget allocations in mind, let's start to look at the reasons for the shift to data-centric AI. So first, what is data-centric AI? So if you've been in the machine learning community for a little while, you've probably seen one of these types of diagrams here and probably been exposed to it a little bit. And ultimately, they're all saying the same thing. Data-centric AI is centering your development focus on the data rather than the modeling techniques. And this really means that improvements on the data are going to result in better improvements in our end model and in our end AI solution than improvements with the same data and improvements on our model. So the reason that this is important is that this actually matches where people are wanting to spend a lot of their money inside of these budgets and inside their companies. They realize that data is really where the bang for the buck comes from. And so focusing development efforts on this data is yielding more results than spending more time iterating on the code itself and the modeling technique. So why is this move to data-centric AI important? So if we think about it kind of more broadly, in any scientific endeavor, you have to isolate some variable to understand the effects of the changes on that variable. So in academia, which is where a lot of the machine learning things tend to come from, for the techniques to be compared to each other. So my ResNet versus my GoogleNet versus AlexNet, all these different types of things. In order to compare these techniques to each other, usually the data set is the simplest and most common thing to isolate. This means that because data can contain a myriad of variables, so it makes sense to isolate it. But in practice, when we're actually trying to achieve a high quality output for the problem as a whole, ultimately, we want to iterate on the thing that's going to provide the most value. We're not trying to compare one model to another model, although that's very useful. What we want to do is take a very, very strong modeling technique and approach, and then optimize the data and iterate on the data. And that's going to end up giving us better results. And whatever gives us better results is ultimately going to be what wins, because it's the output that matters. And for right now, many of the modeling techniques that have come out are very, very good. And this is great. People in academia and research have done an excellent job producing these models and these techniques. But really iterating on the data is what's going to get us further, because there's so many state-of-the-art approaches and techniques that have gotten us so far. And we can take some of those out of the box and then iterate on the data for our particular needs. Now, this also doesn't mean that you can just start with anything and just start iterating on the data. You still need a reasonable model and hyperparameters as a starting point. And so you're still probably going to have to do some parameter search and that kind of stuff as well. But the ultimate thing is machine learning is really 100% dependent on the data. So for instance, even in humans, we don't always understand what the data is, but we can iterate towards understanding our data. And we're not always going to, we understand the data better than we understand what our models are learning from that data. So iterating on the data tends to make a lot of sense in many areas. So what I want to focus the bulk of this time talking about is some practical steps for data-centric AI. So if you've kind of been tracking along and think, yep, this is a kind of an accurate representation, AI today is kind of increasing in quality and amount of investment, and people are interested in iterating on the data because it actually leads to higher quality outputs. This has also kind of been my experience as well. But when it comes to practical steps for data-centric AI, so many of the problems are very different. And this is why I put this comic right here. There is no one size fits all for here is this one tool and it will solve all your problems. Here is this one set of practices and it will solve all your problems. So instead, I actually I think it's a lot more useful to realize that that machine learning development, AI development is not a one size fits all problem, but rather what we can do is learn or take a series of principles. And a lot of these I'm pulling from my own experience, and we want to apply these in the way that seems most accurate for our own data sets and for our own modeling techniques, and even our own production practices. Because things are going to be really different. If you have an offline batch system that's predicting on data, you should structure that probably a lot differently than if you're having an API-driven model that's being served up for like streaming or just like an API REST endpoint or something like that. So yeah, that's why I think the practical steps is really should start with the principles first. So before we jump in, I want to tell you a little bit about my background, because this will give you a little bit of insight on why I think, how I think about the problems, some of my experiences that may make more sense. Because I feel like kind of some of the case studies for moving through things, or being grounded in a case study is more useful for moving through principles rather than just abstractly talking about them. So for me, myself, before I joined Pachyderm, I was director of applied research at a company called Digital Reasoning, and we were working on building speech and NLP models for the financial industry. And so what this meant is we were constantly building out lots of different types of models. We frequently didn't have access to the data externally that clients were producing and everything. And these are being deployed into very, very rigorous environments with a lot of regulation and all kinds of other stuff around what these models could have in them. So we were trying to do really, really sophisticated, cutting edge, like deep learning approaches to some of these problems and apply them in very restrictive industries, which is a hard set of problems all around. So a lot of the things that we're going to talk about are going to kind of center on my experiences through that. So the first principle I have here, and I think and the reason it's number one is because I think it's probably one of the most important. If you're using machine learning to solve a problem, then it's probably not a simple problem. So you shouldn't expect to be able to solve it in just one fell swoop. So my number one principle is set yourself up for iteration. I think about this with myself when I'm writing software, when I'm iterating towards a product. And this has also been seen all across the kind of the DevOps approaches and principles that have existed in software for quite a while now. Basically, it's the idea that we're going to learn more about our problem with every small success and failure. And so this lesson, I'm kind of pulling it from agile development, is just don't take a Hail Mary strategy to solve your problem. You want to split your development into sequences of repeated cycles, and you want to iterate towards accomplishing the bigger task. You want to iterate towards accomplishing the small tasks and compose them together to solve your larger problem. The goal is to get something out the door that works on real data, and then refine it based on customer feedback or how we're seeing the model performance and those kinds of things in the machine learning realm. But so DevOps, this is kind of a known quantity. There's been tons of studies on it. Pretty much every software industry and likely everybody who's listening in has used this to some degree or another. But the biggest difference when it comes to a data-centric approach is that instead of just a single iteration on the software development lifecycle, there are actually two development loops. You have your code development loop and your data development loop or lifecycle. And both of these are crucial. So for instance, the data lifecycle, it's actually a topic that I mention in a lot of the talks that I do. So I won't repeat a ton of it here. But the key is that the data loop or the data lifecycle must be treated with as much care as we're treating our code. So any way that you can think about how you treat your code, so versioning and Git and CI/CD and all these different things, all of these things also likely need to apply to your data as well, because data really is our new source code when it comes to machine learning. So any way you plan to iterate with your data, you should consider how you're versioning it, how you're testing it, what's your release process for your data and data sets. How are you going to go through the process of releasing this? Who's going to have access to it? All the governance things that come with that. So all of these things lead to be able to iterate on your data with ease and minimal risk. So for instance, if you're thinking about how you're going to release, in my case, how I was going to release or work on a financial compliance like voice surveillance situation, then this is crucial because we need to know what data we trained on, what biases exist in our root data, and what's going to end up impacting the output. How are our transcripts going to look on client sites? What's going to happen when we run into accents we haven't exposed our model to? Is it going to predict all kinds of things that we wouldn't necessarily want? There's a lot of things that go into this, and treating our data with care and iterating on it because we know that we're not going to get it right the first time is really, really crucial. So to kind of extend this a little bit more, so in my case, we were working on voice surveillance to find insider trading and market manipulation and these kinds of things in investment banks. And when we were working on this, we were really early on we're kind of like some grad students. We knew machine learning. We had jumped into developing a system for this company that was doing these things. And as we were working on this, we were kind of trying to figure out this one fell swoop. So this is the case where we did not set ourselves up for iteration, and it came to bite us, and we learned this setting ourselves up for iteration is really, really key and important. But we were software engineers. We knew how to work with code, but data, it was kind of a bit of a new thing. We were trying to figure out how to handle it. We were using some deep learning-based, character-based machine learning models to do the voice transcription. And we had a few data sources that we had pulled from the internet. And we were just really interested in solving the problem. And so what we didn't think about is when we pulled this data, we thought, you know what, let's just save ourselves a step and let's just do all of our conversions to normalize our data while we're doing the scraping, because we've already got access to the data. That's just going to be way easier. But the problem was we never really thought that we would potentially iterate on the curation of this data. We figured, oh, there should always be a one-to-one mapping from the transcript that we have to the audio file that we have. We never thought there would be a lot of ambiguity kind of in some of the transcript data, which seems like a silly thing, but I see this all over the place. There's kind of this assumption that our data is going to be gold and we're just going to do some quick conversions on it and then train a model and everything's going to be perfect. But like in this case, even just converting numbers, which seems like a very simple step, like the 2008 results for Q4, there are so many different ways that those numbers can be represented in speech. And because of that, it really depends on what's in the audio file or even how you want to represent what's in the audio file. So we learned pretty quickly that we had to set ourselves up for iteration on the data. We needed to pull the raw data and we needed to version it. And we needed to be able to have these transformations or our data pipelines that curate our data sets be not only reproducible, but something that we could iterate on and know where we've come from for previous models and have a full lineage of everything that we had done along the way. And so this principle itself is how I guess I was first exposed to Pachyderm, where I work now, and how important it is to have reproducibility, data pipelines, and even data versioning as core competencies whenever you're iterating on data. So this brings me to the second principle. Great tools help you make great products. So I usually ask if I'm in a larger room and everyone's present and right there, how much time has anyone spent on debugging a tooling choice rather than actually working with the tool itself? And if you're like me and you've done, I don't know, some amount of work in Jira or other things, then you realize that there's a lot of time that can be spent debugging tooling or trying to figure out how to get that tool to work rather than actually using the tool to get work done. And so all this to say, choosing the right tool is absolutely essential for actually being able to create a good product. So spend the time to choose your tools correctly. Every line of code that you end up writing to overcome a tooling choice is going to become a hurdle. It's a piece of sand in the gears of the engine. And so you're going to have to figure out how to maintain that data, how to maintain those tools and how to maintain the integrations between these tools. All of these things are really, really important to think about up front, because these great tools are really going to be crucial for how you're going to make a great product. And we've really learned this from software as well. So if we look at the software development tooling, these have been iterating and growing for years and years and years. From Linux to VMs to Docker to Git, all of these things come together, and having the right tool chain and the right stack of tools that we're using is going to help us make great products. So for me, or the story from my own life is I started off as a machine learning research engineer. I moved towards doing more applied research, so figuring out research techniques to solve problems in the machine learning world and applying them to different banks or different situations, and then ended up becoming the manager of the applied research group and then the director of the applied machine learning group more broadly. And so what I realized is when I was heading up 3 teams in this case, so there was a data strategy component, there was a data science component, and even a research engineer component, we realized that our group had begun to grow, both in responsibilities as well as the number of people. So I needed to focus more on how the pieces fit together, both logistically and practically, and how to get communication as well as data to pass between these different groups, and even research code to pass between these groups. So for instance, in my case, the data strategy team was responsible for the quality of the data and producing data sets and curating and releasing the data sets. The research engineers were developing techniques for how to best train models on these different types of data sets for these different problems. And our data science teams were applying these research techniques and like pre-trained models and tuning them on customer sites. So there was kind of these distinct groups, but they had a lot of overlap. And so what I needed to focus on was how these pieces fit together. And we formed these different groups to handle these responsibilities, but we needed tooling to be able to pass information and to have a single source of truth for the things that were built and used and released. So this is actually where we started applying Pachyderm, where data sets were consistently curated and pulled and scraped and sometimes like purchased and all these different things. They needed to go into a single place. And for us, that was Pachyderm, because Pachyderm can do data versioning. And then the research techniques, we deployed these as pipelines. So we could always have these ready to release data sets, but we could also look at the different techniques and approaches that we had and see how changes in the data sets or changes in the data strategy affect the research techniques. But we could always go back. So we had a full data history for the data repositories, or for how the data was stored in data repositories in Pachyderm. And then we also had these development techniques that they could iterate on the code and the techniques and produce outputs. And then data scientists could actually look at the dashboards and see how these different techniques were impacting models and decide which techniques were the right ones to apply on customer sites, and also which data or feedback to the data strategy team, which things needed to be curated more, and how we could actually iterate to get things better. So Pachyderm was really nice. It provided a single source of truth. So before working at Pachyderm, I used it and it was great. And that's why I moved over to working for them now. And this is also another thing. So I've mentioned Pachyderm as a single component, but frequently machine learning development and just overall production tooling, or just machine learning tooling itself, it kind of ends up being a full stack of things. There's no one tool, at least in my experience. There's a lot of that are trying to do this, but there's no one tool that fits everything. You're probably going to have some data engineering or some training or some deployment engine and these are usually not all going to fit nicely together. So thinking about the full tooling stack and what's compatible and what's not is really useful. And so this is an example of how a few different open source techniques can all fit together to provide a full stack. And this was created by the AI Infrastructure Alliance. And they're trying really hard to figure out what is this canonical stack, or these sets of canonical stacks that can solve a lot of problems in the tooling world for machine learning. So the third principle, and this one's a little bit of a mouthful, is make it easy to write, test, run, and reproduce your analytics. So overall, this is a tool. This kind of connects to iteration as well as the tooling, because you want to be able to create things, but you also need to be able to have them be reproducible in different formats. So this is probably too many words for everyone to read on here, but basically this comes down to data pipelines. And this is a pretty consistent conversation of what should the data pipelines look like. You can, if you create this giant house of cards from a bunch of random scripts, that's great. It accomplishes something. But if it's going to collapse, if no one else can run it, if it's really brittle, then you're going to spend more time. This sort of goes back to the tooling conversation. You're going to spend more time just trying to maintain that thing rather than use it to actually create value for your company, and even for creating models and providing value overall from a machine learning perspective. So reproducibility and simplicity are keys to being successful. And this has even been the common theme throughout software development. For instance, Linux philosophies of making analytics do one thing well, make sure they can be tested. So what all this ends up leading to is you need to have a strong opinion of how to package up your software and how to package up your models and even experiments, so that they can be reproducible or have them already be captured whenever you created them, and be able to share these or deploy these in different ways. So usually there's a few different layers to this. Sometimes people take the abstraction of just like a pip requirements, and that can be great unless you're dealing with system level dependencies, in which case sometimes people can go to Conda, or even more so, I think Docker is probably best for packaging things up. So for instance, in a Docker environment, it's more or less like a lightweight VM. And I've become a huge fan of that, because when it comes to scaling, Kubernetes is kind of becoming like the most common way to deploy out not only model training jobs, but even your serving and everything else. So the more that you can abstract on top of Docker and Kubernetes, I think this is a really important thing if you're trying to scale up. It might be too much for some teams who are in the smaller growth stage and you have like one or two data scientists. That might be a little too much, but I encourage, as early as you can, start looking at what tooling, how you're packaging things up, and how you're making things reproducible. And so From the Pachyderm perspective, all of our pipelines end up being Docker containers so that it holds all the system dependencies, all the different things that you would need to execute that pipeline job, all in the same place. And this is crucial for reproducibility and even lineage. So this is, I guess I've talked a little bit about Pachyderm. This is kind of the, in my opinion, like one of the things that makes it make the most sense. So Pachyderm itself is two things, and we've kind of alluded to them. There's data versioning, and then there's data pipelines. And so how this comes together inside of Pachyderm is that all the data that goes into our data versioning system, so is organized into repositories. So similar to Git, but not using Git itself. And so you can iterate on the data that's in those data repositories. And then the cool thing is what we just talked about, our Docker pipelines, so the Docker-based pipelines hold our code and our transformations. And so these pipelines can be connected to raw data sets or our data repositories, and they can be essentially a pub sub or like event-driven architecture. Whenever our data changes, we can automatically kick off those pipelines. But if we ever change our code or update our code, our system will realize that, our code has been updated. So the data that has been run on it before is invalid. We need to actually produce a new output. And the output is also versioned, and you kind of daisy chain it along the way and have this full lineage of everything that's ever happened in your system. And so this is really, really powerful. For me, we were doing this with speech recognition data. So Pachyderm can work with any data type, audio, transcripts, video, images, anything, and scale up to any size. So we had probably nearing on a terabyte's worth of audio data that we were training on, or definitely in the hundreds of gigabytes when I was there. And we would constantly be iterating on our cleaning jobs and our model training jobs and how we were releasing those data sets. And so this gave us a single source of truth for how we were able to iterate on the problems and solve each thing. So the fourth principle, and there's only 5 here, so don't worry, we're not going to go too long. And I know we're nearing the end of time as well. So solve one problem at a time. So errors are usually made if you're trying to solve too many things at once. This kind of follows the Unix philosophy to make each program do one thing well. And I've really seen this in particular in computer vision, or just even in speech recognition as well, where you give people too many things to label. And if you're trying to do too many things at once, for instance, if you add too many classes at once with a large variety of objects, then labeling becomes tiresome and more error prone for the people that are working on it. And you're going to see errors across the board. So things don't always stack linearly. We need to be able to execute on one problem at a time and solving one thing well, and then iterate to adding more and more complexity. And then the last principle that I have here is quality is everyone's responsibility. So if you notice an issue in the badly labeled data, I think this goes back to the tooling thing, but you need to be able to fix it. This does go back to setting yourself up for iteration and setting yourself up for having good tools to be able to iterate on things. But you wouldn't set your code up to not be improved or to not be iterated on. And so you shouldn't set yourself up to have your data be fixed and not iterated on as well. So the concern here is that maybe it can cause issues with your data labeling teams, but you need to have review processes. You need to put tooling and review processes in place to make sure that you can submit changes and fixes and review and merge these different things to achieve like a high quality. Because sometimes my research engineers would notice an issue. Sometimes the data scientists would notice an issue. And we really achieve quality when everyone is thinking about the full problem, not just their one particular thing. And so this means communication and transparency has to happen across your full team that's trying to solve a problem. You need to be able to describe how you're going to solve tasks transparently, and don't black box your team's work, which I know is a common pattern, and I can talk a lot more about that one. So projects can frequently go off the rails if people aren't communicating with each other. So with that, that's pretty much it. I'm going to do a quick recap here. So why data-centric AI, iterating on the data gets you further quicker. And there's no one size fits all for machine learning problems, but we can learn to apply these principles to set ourselves up for iteration, use great tools, make it easy to reproduce your analytics, solve one problem at a time, and focus on quality as a shared initiative and not just a single team's problem. So with that, thanks everybody. I think we're right at time, and I didn't see many questions come in. So yeah, thank you everyone for your time, and I'll stick around for a minute if anybody has any questions.